Hello, everyone. Thank you for coming to this webinar on hydration and thermal stress modeling in mass concrete with COMSOL Multiphysics. My name is Tamaskin, and I'm an application engineer with COMSOL Multiphysics, primarily specializing in structural mechanics. Today, we will be talking about a really multiphysics phenomena. Some of you might already know that you can use COMSOL to model all kinds of physics problems going from fluid mechanics, electromagnetics, heat transfer, structural mechanics, chemical and reaction engineering, and acoustics. You can use this tool to model any of these problems on their own. But of course, our biggest point is also that there are built-in couplings that can seamlessly help you integrate more than one disciplinary area, such as fluid flow with heat transfer if you're modeling an isothermal fluid flow, or heat transfer with structural mechanics if you're modeling thermal expansion, which we will talk about today, or structural mechanics with acoustics for structural acoustics interaction problems. Apart from this, we also provide an equation-based modeling environment where you can type in your model as a partial differential equation, ordinary differential equation, or algebraic equation. Of course, all this other physics as well. Behind the hood, they are solving some sort of PD. Now you can add your own equation to model new phenomena or something you're investigating, solve those equations on their own, or what is more interesting is you can couple them with any of the pre-existing physics-based interfaces, as we will see today. Apart from that, you can use the tool to design optimization. Instead of asking, I have these parameters and inputs, what do I get? You can ask the question, this is the result I'm interested in, and what should I do? Kind of design questions. And then there are tools to integrate it with MATLAB, Excel, or CAD if you have your geometry, say, in SolidWorks, AutoCAD, or another geometry package. So that's the COMSOL multiphysics part. As we will see later on, you can also build your model, encapsulate the expertise you built into an app, and share it so that somebody with not necessarily the physics or engineering expertise you developed or the finite element analysis skill can still solve physically interesting problems relevant to them based on what you decide they will be able to do. So today we will be talking about structural mechanics, heat transfer, chemical reactions. The chemical reaction part, we will do it a lot with using equations directly, but then we will point out what you could have done if you are doing a more fundamental chemical analysis for what is involved here. So what I'm going to do today will be divided into three parts roughly. The first part is I'll talk about the fundamentals of this problem. This is thermal expansion in a concrete, but the temperature change or the temperature gradient within the material that leads potentially to thermal cracking is driven by heat generation coming from hydration in the concrete. So we need to know how to model thermal expansion. We need to know how to model the heat of hydration and how to couple all these things together. That's the first part. Then we will talk about a little bit more extensions instead to use more chemistry, to use chemical thermodynamics and reaction kinetics to do more than what we will demonstrate today, to include moisture transport in solids, which we will be ignoring today. And we'll be using elastic behavior for concrete in the demonstration, where we'll talk about what else you could have done to do more fundamental modeling or modeling that follows more to building codes, such as the ACI code. That being the second part. And finally, we will talk about some utility tools which will make this kind of modeling in COMSOL easy when you're using it for yourself or when you're going to share it with other people. I will take questions after the first demonstration. I will pause for questions. Please feel free to type your questions in the chat window throughout, but when I pause there, I'll take the questions that have been typed in earlier or that were typed when I pause. Then at the end, we'll also have a Q&A session. So feel free to ask questions. Now, the COMSOL product suite is Modular, you have the base COMSOL multiphysics package that takes care of basic functionality in every physics area, and then the add-on modules to do anything specialized. For today's presentation, the relevant modules are primarily the structural mechanics module that we need for thermal expansion simulation. If you're going to account for nonlinear material behavior, you might want to go with either the nonlinear structural materials module or the geomechanics module. Both of them basically contain a lot of inelastic nonlinear material behavior. The difference being the geomechanics module is more tailored toward geomechanical applications, soil and concrete, whereas the other one is more towards metal plasticity and hyperelasticity in rubber, but they share certain similarities. And then if you're going to include heat transfer and moisture transport in building materials, there is the heat transfer module. Instead of using the equations, we will type of modeling using typing your equations, as we will demonstrate today. If you are going to be using the built-in chemical and reaction engineering capacities, there is the chemical and reaction engineering module. All right, that said, let's go to the first part. What do we want to model? Now, two things, thermal expansion and heat of hydration. The thermal expansion part, if all you need to do is to add solid mechanics, heat transfer, I will demonstrate this, and then the thermal expansion multiphysics coupling, which takes the thermal strains and puts it into the structural analysis. Now, if you're using, you have a choice of small strain analysis where the elastic strain will simply be the total strain minus the thermal strain, and then the elastic strain will now be used in the constitutive behavior to calculate the stresses. If you are using large deformation analysis, geometric nonlinearity included, then it's the deformation gradient, which will be multiplicatively decomposed into an elastic part and a thermal part. And the thermal part will basically be the identity matrix plus the thermal strain tensor, because here we just don't have shear strains. Okay, coming from the temperature, I mean, of course, there will be shear strains coming from the mechanical loading. All right, that's the first part. And then the next part you want is heat of hydration. Now, for the heat of hydration part, we use the heat transfer interface. It's solving the heat transfer in solids equation, this diffusion equation. Now, the important part as far as today is concerned is determining this heat source. There are several approaches. We'll be seeing three possible approaches. One is to directly assume you know that value. You can say heat source, heat generation rate is given by this function as a function of location and time. You can have an explicit analytical function for this, or you could have data, interpolated data that you can import. But in any case, you know the function. Now, it's rare to know that. If you know that, it's a more simpler problem. The more fundamental thing to do is to model the chemistry directly, where you're going to be finding the heat of reaction from the enthalpy of formation of every product and reactants involved, and using the stoichiometry, and then also doing reaction kinetics to find the rate of reaction. I will spare you those equations for now until later. I'll show you where that can be added if necessary. But a more, what I would call intermediate approach here is to do a kind of a curing equation where you have this variable, say, alpha, which stands for your rate of curing, and your heat generation rate is going to be a function of the rate of curing and the heat of hydration. And then, of course, it can also be a function of temperature and activation energy. Later on, we will see how to add the Arrhenius equation here. There are different approaches, but generally, you can say they look like this. Q as a function of HR and the rate of change of alpha, the curing rate, and that now you need to solve a differential equation at every point to get this. You are not really talking in detail about the chemistry, but you're saying, I can imagine an internal variable which stands for the rate, and I can use this to get the heat generation rate. So now we will be using the heat transfer in solids interface, the structural mechanics, solid mechanics interface, and then an ODE solver for solving the last part. Okay. So then the problem we will be solving here is the solid mechanics part and the heat transfer part, the usual equations. This is the Arrhenius equation developed based on collision theory. There are other similar equations. Maybe you will come up with one in your work. In this particular equation, you see the effect of temperature, activation energy, and the degree of curing on heat generation and the curing rate itself. Since the temperature varies from point to point, the heat generation and curing rate are going to be heterogeneous as well. That is why instead of using the global ODE interface, we will use the domain ODE interface to solve for a distribution. Now I will show you how to do this. So I have this really simple beam. Of course, you guys are going to be using complicated geometry, dams, and other things, but let's keep the geometry simple for the sake of demonstration. I'm going to add some physics. Let's say, come to the physics menu, add physics. If I go to heat transfer, I need the heat transfer in solids. I add that. I'm also going to need the structural mechanics, solid mechanics. I'll add that. And then finally, if I go under mathematics, I'm not going to be using the PDE interfaces because this is a point-wise equation. Every point has its own ODE in time, no spatial derivative in that last equation you saw. So we'll see domain ODE and DOE. Add that. Okay, we have added everything we need. So let's add materials. If I come to materials here, add to materials, under built-in, let me add concrete. Just taking the material from our library, but later on we will come back to when you might want to change this. What else do I need to do? Well, I just said I'm going to do heat transfer, solid mechanics, and a domain ODE for that curing equation, but now I have to provide boundary conditions and initial conditions. So I have certain parameters here under global definitions on the top, parameters under it that I have defined some parameters for initial conditions and ambient temperature and other things like that. So I'll just use those. So in heat transfer, I'm going to have a heat flux. Right click, heat flux. Let's say all surfaces are exposed, and I'll say all boundaries. And then I'll use a convective heat transfer coefficient. Now, what is the heat transfer coefficient you're going to use? This really depends on what you have on the surface, on the condition of the framework, the formwork. Let's put a number there. And then the external temperature, I can type this in, or I can say take it from the ambient temperature. Now that ambient temperature, I will call T ambient from my parameter list. Okay. The other thing I need for the heat transfer part is the heat source. But for the heat source, I actually need this domain ODE, so I will skip that for now. So doing the basics in every physics. The solid mechanics, let me say I have fixed constraints on this face, on this other face. If I have any mechanical loads, I can start adding them here. prescribe displacements, or if I can volumetric force, gravity, other things. But let's say I'm just considering the effect of temperature. So I have no mechanical loading. Later on, I'm going to be doing a dynamical analysis. For this problem, the inertial part isn't that important, so I will do a quasi-static analysis. The next part in this physics is this domain ODE part. So let me go back to the equation. This first equation is what I'm going to enter. Rate of change of that curing variable is given by this. So what is that? First, I will give it a name. COMSOL already called it U2, but I want to call it alpha. It's a dimensionless parameter, but the source term is 1/2. All right, then the distributed ODE. What is this equation? If I expand this second order derivative is not there in the equation here. I only have that first order derivative with a coefficient 1, and then I have the source term given on the right hand side. So I'll type in the source term. Source term is A times the exponential of minus the activation energy divided by that gas constant divided by temperature. Of course, this temperature would be different at different points. So this will make a highly nonlinear problem. If you think the temperature is constant everywhere, that will be a very simple problem, but you don't see the effect because the tracking is often motivated by a temperature gradient. And then 1 minus alpha raised to n. Okay. What else do I need? Of course, the damping coefficient, I keep it at 1. I don't have the mass coefficient, the second order derivative not being involved here. The initial values, if I am starting from no curing at all, then I will leave it at 0. Okay. Next item. Next item here is the heat source, right? We have this last equation. So if I go back, heat transfer in solids, heat source on this domain. This is going to be, we're going to be entering this directly. Later on, I'll show you how to grab it from another physics. But here, we have the density, solid dot rho, multiplied by this parameter, multiplied by alpha being the primary variable, alpha t will be its partial derivative with respect to time in the COMSOL terminology. Okay. What remains now is that multiphysics effect. So I have coupled this curing equation with the heat transfer, but there is the solid mechanics part. Granted, this being a small deformation problem, and the solid mechanics doesn't have any effect back on the other two, so I could first solve those two and then use that result to do solid mechanics, thermal expansion, but I could also solve them all together. Thermal expansion in this domain. I have to specify the reference temperature. Let's say that's my initial temperature that I have parameterized. That takes me back actually to the initial values to temperature instead of this room temperature. Here I have used around 15 degrees Celsius for this, but it's basically the temperature of the concrete when you lay it and before you start this process. All right, I have all the ingredients I need here. The next part is to add a study. So if I go to the study menu, add study, I'm going to be doing a time-dependent study, so I pick time-dependent. I'm going to solve this for a week, let's say. So it's easier if I put in the units in time, up to 7 days, but let's say every hour, something like that. Then we solve this problem. Now, there are some things that I want to monitor while I am solving. For example, let's say I want to know if the tensile stress is going to be higher than a certain amount, and I want to see it while it's solving. So if I say show default solver to get a data set, and then under result, I can add a 1D plot group. Let me call that maximum first principal stress. Under it, I'm going to be adding a global item. This is going to be the maximum of solid.sp1. This is COMSOL terminology for first principal stress. Then I can come here and then say, while I am solving, plot this. Now this will take me some time, so instead of solving that, I will switch to showing you a result from a backup file. Okay. So what do I have here if I solved it? I want to see the temperature at different times. If I go back all, this would be at the beginning, and that would be at the end. You'll see that the internally it's hotter and then it's colder outside. Let's say I want to see the principal stresses. Here I see the principal stresses, the first principal stress, but I could also see another quantity, the bonus stress, for example, but I'm more interested in whether there will be tension, a high tension, then I'm more interested in this. The temperature difference, some people like to say, oh, when the temperature difference is this much, that's when the situation is critical. So I can look at the temperature difference between the coldest point and the hottest point through time, the maximum tensile stress, what is the average heat generated, things like that. We could be asking, for example, this is my average heat generated for this example. Now, this depends on a lot of factors, right? On the curing rate, on the heat of hydration, on the ambient temperature. So later on, we will see. Okay. That said, I will take questions if you have any questions so far. Okay, I have a question here. How do the solid mechanics physics differ between the base COMSOL product and the structural mechanics module for linear elastic isotropic material? For linear elastic isotropic material, in terms of the constitutive behavior you can capture, there is no difference between the base product and the structural mechanics module. What will differ is, for example, in geometric nonlinearity, for example, you could have a linearly elastic material that's going large rotation or large deformation, then you might want to consider finite strain effect, right? If you're doing anything like buckling analysis, that's going to be important. So those kind of things are not available, but if you're just doing a stationary or time-dependent analysis on linear elastic materials, not just constitutive linearity, but geometrically linear as well, then there's no difference. Another question here, where do you enter EA? Oh, I entered them here under parameter, global definitions parameters, I entered them there. Another question is, can you comment again on why the domain ODE and DAE is appropriate here? You mentioned no special variation or something. Sure. If we go back to the equation here, right? for just the curing part. What you have is the rate of change of curing is proportional to something that is happening just at that point, right? Yes, it is varying, but it's only varying in time at a given point. There is no effect like diffusion or convection, right? If you had diffusion or convection, you'll get partial derivative with respect to space in your equation. But here, this is a kind of a material evolution equation that's just at the point based on the current situation at that point. So you don't get any special derivative for this particular equation. I mean, you could add the PDE interface here and put all the terms like the mass terms and the stiffness terms to 0. But I mean, the stiffness terms to 0. But why would you do that, right? You're basically building up a whole matrix of zeros that you're not going to need, but it will be inefficient. So it's more a matter of efficiency than accuracy here, actually. Okay. What is the discretization order you choose from the domain ODE? Here, I left the regular, I use the default discretization, but if you come here, you can choose between Lagrange and Hermite and other shape function types. So the software defaults to a certain order of approximation for every physics. For example, if I come to solid mechanics, the discretization is going to be picking quadratic serendipity. But for another problem, it can pick a different one. If you really want to change it, you can change that, but usually the default is good. Okay, so let's continue. Now, what could we have done more here? I'm here basically telling you all the tools you can have without really going into too much detail on any specific subject. It's a very multi-physics problem, and it's a very still active area where people have a lot of questions. So we want to provide you all the tools that can help you experiment and numerically things that you cook up in the lab or from your theory. So what extension could we have done? The first thing we could have done is going to the chemistry part, right? Here we really ignored the chemistry and picked, I mean, not really ignore, but we didn't directly model the chemistry. We just took the curing equation. Now, if you use the chemistry from the chemical and reaction engineering module, one thing you get here is first the chemical thermodynamics and kinetics. So if you come under here, what you will find, the first one here is reaction rate, rate constant. So here, for example, the reaction rate is based on the stoichiometry, the enthalpy of reactions. Here, this will be based on the stoichiometry and the enthalpy of formations of each, which here I just took this to be a variable, right? A parameter that I know, right? Heat source, what do you do here? So these are all there. Then the next thing is, if you go to the heat transfer, then the heat transfer part will actually give you a heat source that you can use. Okay. Another thing I could have done here is, before doing that, let me show you where you could have added this, right? If you go to component and add physics, chemistry, add that. Once you add that here, you can add different species. You can keep adding the species name. You can type your reactions. And then here you have basically where it calculates thermodynamic properties, transport properties, mix properties. if I add a reaction, then here is where you can type all kinds of reactions, fill in more. Okay, but then in heat transfer, that would calculate the heat source for you. I have a question here. I think the rate of hydration depends also on the amount of cement that you use in the concrete. Is there any way to account for this in the model? Yeah, that's a good question. If you actually look at this slide that I have up, the second image, if you go there, you have the reaction rate, Rj, given by this, and this Ci's here are concentrations. And then, the Hj here is, of course, coming from thermodynamics. So you have the thermodynamics part here, and then upper here, the kinetics part. And then the kinetics part is a function of the concentration. So you can have different species, right, inside in this mix, and the concentration of each mix. If each species will affect the reaction rate through the reaction rate. Here, the last equation, Qj being Rj minus Rj times Hj, that rate, which is a function of the concentration, now affects the heat rate. Yeah, you're right. So if you go there, you could do all this more fundamentally. So in the model we used earlier, we kind of glossed over this and did the one item, one kind of internal variable that encapsulates everything. Another thing that we could have added here is the moisture transport part, moisture effects on thermal behavior. You also might want to add swelling and shrinking induced strains through the hygroscopic swelling feature in COMSOL. Another thing you could have done is to model the constitutive behavior of concrete better. If you're using nonlinear or inelastic behavior, you already have this, for example, from the geomechanics module, constitutive behaviors that are more suited to concrete. You can use that. Another thing would be to model damage. Now, sometimes you have building codes that specify this is the stiffness, material stiffness the elastic modulus you should use as a function of time. This is because we really don't, if you don't have a fundamental mechanistic model, but you have done experiments and you have seen how it varies with time, your strength. So when it's setting, your strength could be increasing with time, but then later on, it could be decreasing or getting damaged. So the simplified models just give you this as a function of time. In that case, you just, if you remember the COMSOL technology, every place you could type a number, you could type an expression. So you can come here and you can expand this. And if you go to Young's modulus, for example, you can start typing a function, an expression that contains t or another function of t. That way you do this. A more mechanistic approach would be to do the constitutive model behind this instead of just saying, this is it. So if you go to this link, for example, you will see code that will let you add a damage, that demonstrates how to add a damage model. What else could we have done? Now, those two were for physics-related things. But now I would go into more utility tools in COMSOL that will make things easier when you build this kind of models. These are stop conditions to stop the time-dependent solver if certain criteria is met. Failure criteria and safety factors, specifying ambient temperature better, and sharing your work. Now, what are stop conditions for? Stop conditions are, just as the name implies, to stop your simulation. Here, I am going all the way to, say, a week. Maybe I can say this will go until 100 days. I don't exactly know when some critical behavior is going to happen, let's say a maximum tensile stress or maximum temperature difference, whatever I want to monitor. And I want to stop. I don't want to solve once that has happened. If I'm not interested in that part, what I will do is I will come to the solver and add a stop condition. And in the stop condition, I can add any global expression that evaluates to 0 or 1, true or false. So when it's true, it will stop. So let's say I want the maximum temperature difference to be limited. I can say, okay, from component 1, that maximum operator, pick temperature from component 1. So track that from the minimum temperature. And I can say if that was greater than 20 Kelvin. Okay, so this evaluates to true or false. And I think I missed. This evaluates to true or false. Then when it's true, it will stop. Or I could change this to say the maximum first principal stress, component 1, the maximum operator that I built of from component 1, solid.sp1. If that was greater than 5, this depends on your concrete grade, stop. Then if this condition is hit in 3 days, it will stop the simulation. So that will make life easier. Another thing that will make life easier is to add a failure criteria and to evaluate safety factors. So if I go back to my model under solid mechanics, I can come here and then I can say, I want safety factor calculation, and you pick your failure criteria. Let's say if I pick this, I can say, okay, I will type in my tensile strength, compressive strength. The equation it is evaluating is this. Now you can solve this. Also, you can combine this with the stop condition. So here you can type this in terms of that safety factor. When this safety factor is violated by this amount, stop the solver kind of questions. All right. What else can add here? Now, this safety factor is a point-wise. Every point, based on the stress calculated at that point, has its own safety factor, margin of safety. And if you are checking, usually you want to check what is the minimum, like the worst situation, right? So you can ask for the minimum safety factor, be something, combine it with the stop condition, and do interesting simulation. Another part is ambient temperature. This is actually pretty interesting. If I go to heat transfer, instead of typing the ambient temperature, I can say get it from a meteorological data. And I can come here and set a weather station. Let's say we are in North America, United States, Boston, let's say. And then now, the ambient wherever you refer to ambient temperature, it will be grabbed from here. If you are running this for a short time, maybe this is all you need to do. But let's say you are running this for a long time, duration, for order of months, the ambient temperature could actually be changing. If you have that ambient temperature as a data, you can just put it in as an interpolation data. But if we want to use meteorological data, you can come here and say, check this on, update time from solver. So what it will do is at every time the solver, when it's at a new time, it will actually grab, if it has to be used, it will grab the current ambient temperature based on the date you specified and the location you specified and where the solver is in time. Okay. The final thing that I will quickly show here is developing apps. Once you have developed app, let me revert to saved. Once you have developed your model, you can say, look, I want to do something here that I can share it with other people. So you can encapsulate your expertise you have built. You have studied the chemistry, you've studied the numerics. I have one form here already. Let me delete it. Let me show you this from scratch. You can say, okay, I want a new form. You decide what people want to see. Are you going to allow them to change geometry? Let's say you want to allow them to just change the width, but not the other things. Are you going to allow them to change, say, the ambient temperature? Maybe you do. Graphics. Maybe you want geometry, and then you just want the maximum tensile stress to be seen. So here you are deciding what your users can see. You want, say, a plot geometry and compute study button. Okay. So then I will say done. I get this. This is very rudimentary. If it doesn't look good, blame it on me. My sense of aesthetics is not known to be that good, or not known to be good. I think I messed that up there. Okay. So if I test this application, I mean, I'm showing you this because most of you guys will be doing some kind of deliverable, like doing consulting work for the government or for a state agency or for private entities. You want to make this, and then now another person can say, okay, I want to analyze this kind of situation where this is this, and click compute. Then they can go ahead and see the result that they want for the inputs they have made. You can put this online as well. So there are information online. We also do webinars on how to make apps. So you can learn more there. So that brings me to the end of the things I wanted to show here. I'll take on one last round of questions. How do you access safety factor variables in post-processing? Okay, let me stop this calculation, the app that was running. If I go to Model Builder, now let me add a safety factor here. And let's say I use this. So there's two things here, actually, I want to show. Say this. Just because you added a safety factor, you don't need to solve the problem again. It doesn't affect the solution, right? Unless you want to use the stop condition on it. It's just checking the safety at every point based on the results you have. So you shouldn't click compute if all you did is just add a safety node and didn't change the other model items. You update your solution just to update for that variable. And then once you do that, in post-processing, if you go under solid mechanics, let's say instead of plotting temperature, I can come here, and if you come to solid mechanics, there is this safety node. You could also have added multiple safety nodes, and they will all show, and then safety factor and plot it. Okay, I have a poll question here that I would like you guys to quickly answer before we part. Thank you for attending this webinar. If you have any questions, don't forget to come to COMSOL.com to contact us, to request a demo, to download the product, to look at user stories videos. We will archive this webinar as well. If there are any questions that I haven't addressed, I will follow up. We'll follow up with you guys in support. So the question here is, we wanted to know which aspect of this modeling you would like to know in detail. 42% said constitutive behavior, structural mechanics. 38% said heat and moisture transport in buildings. 13% said chemistry, and 8% said other. Thanks for attending, and thanks for your questions. See you around.